Welcome to the CSE Colloquium. It's my pleasure to have Franzi visit us, not necessarily visit us, just actually walk down the stairs in some ways. Franzi has done a lot of interesting work in computer security. For the last few years, she's been working with Yoshi Kono on various aspects of computer security. She did the first possibly comprehensive measurement of web tracking, third-party tracking on the web. And she developed tools which people can use as defenses for third-party web tracking. And more recently, she's been looking at how you can actually give permissions to applications running on mobile devices. And that work basically got a Usenix Security and Privacy Best Paper Award. And she's going to be talking about a lot of that during the talk today. So it's without much ado, let me hand over the honors to Franzi. Thanks.
All right. OK, thanks, Arvind, very much for the introduction. I'm happy to be here today, even if it's a little bit strange. Today, I'd like to talk about understanding and overcoming challenges in computer security and privacy for modern technologies. As we all know, and probably the reason that many of us are in computer science, new technologies bring new benefits to almost all aspects of our lives. Just in our lifetimes, technology has completely transformed how we communicate, how we interact with the world, and how we live our lives. And that makes this an extremely exciting field to be working in. But unfortunately, new technologies also bring new and serious security and privacy risks. To give you just two examples that I'll be expanding further throughout my talk, first, the web allows for ever greater invasions of our privacy. And second, if you accidentally install a malicious application on your smartphone, it can track your location and secretly send costly SMS messages. What web privacy and smartphone security, and many of the problems that I'm interested in, have in common is that they often arise because users' expectations about how a system works don't match with the system's actual security and privacy properties. There are generally two strategies that we can take to try to mitigate this discrepancy. On the one hand, we can try to help users change their mental models by helping them think twice, for example, before installing a malicious application. On the other hand, we can try to change systems so that they better match what users already think is going on. Both of these approaches can produce interesting solutions. But in my work, I'm really excited about building real systems. So today, I'll be focusing primarily on the second type of approach. In order to build systems that better match user expectations, my work focuses both on understanding existing user mental models and analyzing the security and privacy properties of existing systems. And that then informs the design of new systems. Simultaneously, I try to anticipate technologies that are likely to become important and widespread in the future. And the goal here is to try to understand and mitigate risks before they become widespread. As you can see here, I'm interested in a broad range of technologies and different aspects of computer science, all under this umbrella of improving security and privacy. Today, I'd like to focus primarily on a subset of my work that both illustrates this general approach and that tackles some of the most important security and privacy challenges that are facing users today. Specifically, I'm going to tell you about two important ways in which user expectations don't match the reality of the security and privacy properties in today's systems. First on the web, and then in the context of modern operating systems like smartphones. Solving that second set of challenges will actually uncover a whole new research direction about security at the level of the user interface. And so I'll focus the third part of the talk in more detail on that. And finally, at the end, I'd like to briefly loop back and briefly tell you about some of the other work that I've done, like on automotive security, or some forward-looking work on security and privacy in emerging wearable and augmented reality technologies. So let me start with the web, a technology that we all use in our daily lives. And I'd like to tell you about a widespread privacy risk that's invisible to many users. I suspect that many of you have had the following experience. You're browsing somewhere on the web. Maybe you go to Zappos to check out some shoes. And next thing you know, the ads for those shoes are following you everywhere you go. So here it is on CNN, and there it is on The Onion. You might find this a little bit creepy because it means that somewhere, someone on the internet knows that you need new shoes. And in fact, advertisers and other entities commonly track your browsing behaviors to do targeted advertising, website analytics, and other types of personalized content. Let me show you a little bit more about why some people consider tracking to be a privacy concern. What you might not realize when you see these ads is that they're not actually loaded from The Onion or from CNN, but from third-party advertising networks. In this case, that's Criteo.com. And what that means is that Criteo can link your visits to these two sites. In other words, it knows the same user has visited both sites, even if you never actually click on any of these ads. As you continue to browse the web, Criteo can continue to observe your visits to sites and build up what we call a browsing profile of you. You might not care too much if Criteo knows that you visited CNN or The Onion, but if you think about your browsing history or maybe someone else's browsing history over the course of the last month, there might be other sites that you're more uncomfortable with some random third party knowing about. In fact, there was a public outcry about these privacy issues back in 2010, 2011. For example, the Wall Street Journal published several exposés about the privacy concerns associated with tracking, highlighting, for example, the fact that advertisers are not only able to track your browsing history, but to infer additional personal information about you, like your age, your gender, or your other interests. In fact, privacy concerns were so high that there was a bill brought before Congress called Do Not Track. And the goal of that bill was to allow users to effectively opt out of these different tracking mechanisms. Back in 2011, when I first became interested in tracking, I realized that although there was a lot of discussion of it, both in the research community and in the media, there was limited understanding of how tracking actually works in practice. And that limits our ability to think about effective defenses or policy solutions. The goal of our work was to systematically study the web tracking ecosystem to inform both the designs of defenses and policy discussions. This was challenging because, like I've already implied, there was no agreement on the definition of tracking, so we didn't really know what we should be measuring. And more generally, there was no automated way to detect trackers at the time. So at the time, the way to detect trackers was to use a blacklist of known tracking domains. But of course, if we really want to understand how tracking works in the wild, we need a way to detect and measure trackers that doesn't rely on this precompiled list. When encountering a new ecosystem like web tracking, a common approach that many security researchers, including myself, like to use is to first analyze that ecosystem. So in this case, I manually reverse engineered the trackers that I saw on the client side, so in my browser. And I used that to develop a taxonomy of tracking behaviors. I'll show you some of the highlights from that taxonomy today. I then built an automated measurement tool to measure tracking in the wild based on that taxonomy and evaluate the effectiveness of existing defenses. And those findings then inform the design of new tools and new defenses for users. So first, a little bit of background on how the web works to make sure that we're all on the same page. The most important thing to know is that websites can store information in your browser in the form of cookies. So here, for example, The Onion and CNN have both set some sort of unique identifier in your browser so that they can re-identify you when you come back. By the same origin policy, these cookies are only accessible to the sites that set them. So for example, The Onion and CNN can't read each other's cookies. And most importantly for tracking, these cookies are automatically included in any requests that your browser makes to load the associated page. Let me show you how these trackers can use this cookie mechanism to create a cross-site browsing profile of you. Again, let's think about The Onion and CNN, but now let's think about what happens when this embedded third-party advertisement is loaded. Again, this ad is loaded from Criteo, not from The Onion or CNN. So when your browser makes the request to Criteo, it will automatically include Criteo's cookie. That cookie will be the same anytime an ad from Criteo appears. And if it contains a unique identifier like this, then Criteo is able to link your visits on all of these different sites. Now, this may seem fairly simple, and in fact, this is what people mostly think of when they talk about third-party tracking. But it turns out that, in fact, in the wild, tracking is much more complicated than this. Not only do trackers use different mechanisms other than cookies to store state, In some cases, they don't need to store any state at all to re-identify you. And furthermore, what I found in my reverse engineering was that trackers exhibit different behaviors. And those different behaviors have different implications for the types of defenses that are effective and the types of browsing profiles that these trackers can create. So I won't be going into the detail of our tracking taxonomy today. If you're interested, you can check out our NSDI paper from 2012. The basic type of tracking that I've already described to you is what we call vanilla tracking. And I'd like to introduce one additional category from our taxonomy to you that I think is particularly interesting. If we go back to this screenshot of the onion, we already know that Criteo can track you through this embedded Zappos ad. But I'd also like to draw your attention to these embedded social media buttons, like the Facebook like button, the Twitter tweet button, or the Google +1 button. You've probably seen these buttons as you browse the web. But you might not have realized that they actually allow the associated social media site to track you in the same way that advertisers do. We call these personal trackers. Let me show you a little bit more how they work. This should look pretty familiar now. The main difference in this scenario is that you sometimes visit facebook.com directly. So when Facebook sets a cookie, it doesn't just contain some anonymous unique identifier, but actually an identifier that links back to your Facebook profile and all of the other personal information that you've entered there. Now when you visit other sites that include the Facebook like button, and your browser loads that button, again, it automatically includes Facebook's cookie in those requests, and Facebook can link your visits to all of these different sites that include the like button. Again, I want to emphasize that this is possible even if you never actually click on the like button. Just loading the button will give Facebook information about where you're browsing. There are a couple of reasons that personal tracking is especially interesting. In addition to not being anonymous, it also allows the trackers to evade certain types of defenses. So in particular, because of some of the quirks of how different browsers implement third-party cookie blocking, which is a commonly recommended defense for tracking, if you visit Facebook or Twitter or other sites directly, they're actually no longer subject to the third-party cookie blocking restrictions. So I'd like to transition to tell you a little bit about the measurements that we did and what we learned about the prevalence of tracking and the effectiveness of different types of defenses. To carry out this study, I built a browser extension that automatically browses the web and detects and categorizes trackers according to their observable client-side behaviors. I'm going to give you some of the highlights from the measurement study, which was done back in 2011. But I actually repeated many of these measurements recently, just a few months ago. And what I found was that the tracking ecosystem has actually not substantially changed since 2011. So the high-level results that I'll be telling you today are still valid. The first thing you might be interested in is how prevalent tracking is. Back in 2011, we found over 500 unique trackers on the top 500 websites. And furthermore, many sites tend to include multiple trackers. In particular, most sites included at least one tracker. About half of sites included between 4 and 5 trackers. And then we have this long tail. In the extreme, we saw one site that included 43 unique trackers. So a user who's visiting that site might be surprised to learn that there are 43 different third parties that have learned about his or her visit to that site. We weren't just interested in how much tracking there is, but in how real users are actually affected. So how much of a real user's browsing history can one of these top trackers actually capture? This is a little bit challenging to measure. One thing we could have done is instrument real users' browsers and gather their browsing histories and then run our tools on that. But that, of course, has some privacy implications, and we might worry that users browse differently when we've instrumented their browsers in this way. Instead, we realized that the AOL search logs, which were released back in 2006 and include search histories, search terms from real AOL users, actually do represent real user behaviors. So we used these AOL search logs to create hypothetical browsing histories for 30 of the AOL users. We took 300 unique queries from each user, searched them on today's search engine, then used the top search result as an entry in their approximate browsing history. And I say approximate because, of course, we don't know that the AOL users would have actually clicked on the top search hit, and today's search engines might give us different results. But nevertheless, the underlying behaviors are based on real user search queries. What we find is that the top trackers can actually capture a large fraction of these users' browsing histories. These are the top 3 trackers in our data set. So DoubleClick can capture almost 40% on average of one of these users' browsing histories. And Facebook and Google, which are both personal trackers, so they might not be tracking anonymously, can capture almost a quarter of these users' browsing histories. Privacy-sensitive users might be concerned to learn that these percentages are so large. And in fact, even users who might think, well, OK, I give Facebook and Google all of my information anyway, might be more concerned to know that we recently learned that the NSA has actually been piggybacking on these tracking mechanisms for surveillance purposes. If we dig a little bit more into who these top trackers are that we saw in our data, here are the top 20 trackers. The height of the bar corresponds to how many of the top 500 sites we saw each tracker on. And the color of the bar represents the type of the tracker. So in this case, I've distinguished personal trackers in red and anonymous trackers in black. First of all, you can see that the personal trackers in red, these are things like the Facebook like and Twitter tweet buttons, actually make up almost a quarter of these top trackers. And furthermore, when we looked at the defenses that were available to users at the time, we actually found something interesting, which is that most defenses were reasonably effective for most types of trackers, with the notable exception of these personal trackers. So you can see only the red bars remain. There's one exception there on the far right. That's a tracking category that I didn't tell you about, and it's still there because of some of the nuances of how it interacts with the personal trackers. In any case, the defenses that were available for personal trackers at the time were either completely inadequate in that they didn't prevent tracking at all, like third-party cookie blocking by these trackers, or they completely removed the social media buttons from the user's browsing experience. So if a user wanted to sometimes click on the Facebook like button, but be protected from tracking when they chose not to click, there wasn't a middle ground option for these kinds of users. That finding led me to design and develop ShareMeNot, which is a browser extension that protects against tracking by these social media buttons without compromising the button's functionality. So in other words, it gives us this middle ground. At a high level, the way ShareMeNot works is it detects requests to load these social media buttons. It blocks those requests and replaces the buttons on the client side with a local version of the button. So that means that users can still see these buttons and choose to click on them. When ShareMeNot detects that they do that, it allows the request to go through to the social media site just as expected. The ShareMeNot implementation is actually pretty simple, but it wasn't until our measurement study that we really understood the prevalence of these personal trackers and the inadequacy of existing defenses. In fact, ShareMeNot's techniques have been adopted in a few places. So for example, some of you may be familiar with Ghostery, which is a popular anti-tracking add-on that has millions of users. It's adopted ShareMeNot's techniques. And the Electronic Frontier Foundation, which is a nonprofit digital rights organization, has recently started building a new anti-tracking tool and is looking to incorporate ShareMeNot as well. In this first part of the talk, I've told you about third-party web tracking as an example of a privacy concern on the web that's invisible to many users. We studied the tracking ecosystem, and we found not only that tracking is prevalent and varied, but that there weren't existing defenses that were adequate for these personal trackers like the Facebook like button and the Google +1 button. And that then led to the design and release of ShareMeNot, which is a solution that makes these social media buttons work in the way that users actually expect. I'd like to shift my focus to another widespread technology, which is modern operating systems, especially smartphone operating systems. Security in the smartphone ecosystem is far from solved. Let me give you a couple of examples of where things can go wrong today. First of all, users are easily tricked into installing malicious applications. Often these apps come in the form of repackaged versions of existing applications. And on the surface, this malware works in the way that the user would expect. But under the hood, it can carry out silent attacks like secretly sending costly premium SMS messages. That's a very common attack. Even legitimate applications can act in ways that users don't expect. Many studies have shown that top mobile applications commonly leak sensitive data. To give you just one example, one study found that almost half of the Android applications that they looked at leaked location information or phone identification information to third-party advertising or analytics servers. These are things that the users of these apps probably don't expect. And the reason that we have these problems in the smartphone ecosystem is not because smartphone operating systems haven't been trying to improve security. A common thing that these operating systems do is to restrict the permissions of applications. So apps by default don't have access to sensitive resources like the camera or the microphone or the ability to send SMS or make calls. Of course, legitimate applications do need access to these resources to carry out their intended functionality. So a challenge faced by these operating systems is how they should grant permissions to these apps to access the resources that they need. Generally, the way that operating systems do this today is to directly ask the user to make these decisions. Let me show you a couple of examples of how systems do this today. If you use iOS or many browsers, you're probably familiar with these types of prompts. This is an example on the top, for example, of an iOS application that is trying to access your location. You probably know from your own experience that these prompts are really disruptive. You just want to click OK to get back to what you were actually trying to do. And in fact, studies show that that's what people do, and so prompts don't provide the intended security benefits. The other common approach is the install time manifest. This is used by Android and Windows Phone. This is a list of permissions that an application requests. And at installation time, the user has to either agree to all of these permissions or choose not to install the application at all. So I'd actually like to take a quick poll of all of you. I'm going to ask 2 questions, so leave your hand up after the first question, and we'll see the difference. The first question is, how many of you use Android or Windows Phone? OK, leave your hands up. Now, leave your hands up if you always very carefully read this list and sometimes click no. That's actually, that's maybe the best percentage I've seen so far. Nevertheless, even with this pretty biased, technically savvy audience, many of you don't actually make decisions based on this manifest. And in fact, studies find that users don't read and don't understand the list of permissions. And it's not really fair to ask users at installation time because they don't yet know how the application is actually going to be using those permissions. In practice, both prompts and manifests are overly permissive. Not only do users accidentally grant too many permissions, but once the permission is granted, it's often for the duration, the lifetime of the application. So they can continue to use the permission even when it has nothing to do with what the user is actually doing in the application. This lack of a good permission granting model is a fundamental problem underlying many of the issues in the smartphone ecosystem. So part of my work tried to devise a better permission granting model to address these problems. If we step back and think about what we would ideally like in a permission granting model, first of all, we would like it to be least privilege. In other words, applications should receive only the minimum access necessary to actually carry out their intended functionality. We'd also like it to be usable. So unlike prompts, it shouldn't be disruptive to users. And we shouldn't be asking users to constantly understand or manage the permissions that are held by all of their applications. One way to maybe summarize these first 2 goals is to say that we want something like magic, that magically does what users actually expect. And I'll show you in just a couple of slides what users are actually expecting here. Maybe a less obvious goal is that permission granting should be generalizable. It doesn't help us a lot if we can come up with a great approach for the clipboard if it doesn't also work well for other resources like the file system or the camera. I'd like to tell you about our work in which we devised a permission granting model that better meets these three goals. The insight underlying what we call user-driven access control is that the way users naturally interact with applications actually already carries permission granting information. For example, when a user clicks on this location button inside the Maps application, roughly what they mean is that the application should access their location now. And maybe equally importantly, if they haven't clicked on that button, the application shouldn't be accessing their location. This is not a contrived example. There are many other examples of resource-related user interface elements that users associate with permission use. For example, if a user clicks on the video call button, they probably expect that the application will access the camera and the microphone. If they click the paste button, they probably expect that the app will access the clipboard. And we already saw this example earlier today of the Facebook like button, which users expect will not reveal information about their browsing history to Facebook unless they actually click on that button. We surveyed users and found that they actually already believe that permission granting follows this model. Specifically, many users already think that, for example, the application can't, or at a minimum shouldn't, access their camera if they haven't clicked on the camera button. Similarly for other resources. Of course, this is not how today's systems work, but it's what user-driven access control would provide. This is a nice idea, but let me show you why it's challenging to achieve in practice in today's systems. Here's a view of a system today. Suppose on the left we have the user's view of the world. They're using a photo editing application. On the right is the operating system's view, which has maybe granted the application some permissions, maybe at installation time, including the camera permission. So the user might interact with this application. They might click on the camera button. That click will be dispatched to the photo editor, and the photo editor can then do whatever it wants. A reasonable thing to do might be to access the camera's APIs and take a picture. There are two important points that I want to make here. The first is that what I've shown you is actually a well-behaved application. There's nothing preventing the photo editor from using the camera permission at any time, even if the user hasn't actually clicked on the camera button. The second point is that it's actually hard for the operating system to enforce that kind of restriction, because the operating system doesn't know and can't understand what the user is doing inside the UI of some arbitrary application. So the underlying challenge here is how can we let the system extract access control decisions from the way that users interact with arbitrary applications. There are a couple of ways that we might approach this. And in fact, we're not the first to think of something like user-driven access control. But unfortunately, prior approaches are often hard to generalize. They focus specifically on one resource, like the file system, or on analyzing the user's interaction with a specific application, like the browser and the browser's file dialog. In our work, we introduced a new operating systems primitive to address this challenge. It's what we call an access control gadget, or an ACG. Essentially, we take these resource-related UI elements, which I've circled here again in red, and rather than letting them be controlled by the applications, we allow them to be controlled by the operating system. In this world, an application that wants to access a sensitive resource simply embeds one of these access control gadgets and waits for the user to interact with it. At a high level, that means the operating system can understand the user's interaction with different ACGs and make access control decisions based on that. Let me go back to our system and show you how that changes when we introduce access control gadgets. Again, we have the photo editing application, except now we also introduce in the operating system this additional application that we call a camera resource monitor. It's the camera resource monitor's responsibility to mediate access to the camera resource, and furthermore, to expose a set of access control gadgets that applications can embed inside of their own UIs. There might be different resource monitors for different resources, so there might be one for location as well, for example. Now here in this example, where before this camera button used to be a button completely controlled and drawn by the application, It's actually now an access control gadget that is drawn by the camera resource monitor and simply embedded by the photo editing application. What that means is that now when the user interacts with the camera button, that click is dispatched not to the photo editor, but actually to the camera resource monitor. And now it's up to the camera resource monitor to handle that click in the way that's appropriate based on the semantics of that button. In this case, that might be to access the camera's APIs itself and take a picture, and then pass that picture on to the photo editor. You'll notice now that the photo editor doesn't have the opportunity to access the camera's APIs out of turn on its own. The camera resource monitor, like I said, is responsible for supporting reasonable semantics. So for example, for a video call button, the camera resource monitor might instead mediate some sort of session access for the photo editor. Introducing access control gadgets into a real system raises some interesting challenges, some of which you might already be thinking of. The first set of challenges relates to the impact on applications. So what about application customization? What if an app doesn't like the set of access control gadgets that are provided by the camera resource monitor? And more generally, can we support the full set of application functionality? These are, of course, issues that we thought about in our work. And I'll come back in just a couple of slides to the question of application customization when I tell you about our evaluation. But for the purposes of this talk, I wanted to focus a little bit more on the second set of challenges, which relates to attacks by potentially malicious applications on access control gadgets. Malicious applications might want to attack access control gadgets primarily in order to gain unauthorized access. In other words, they might want to take a picture or send an SMS without the user legitimately interacting with the access control gadget. One example attack that an application might use to do this is what's called a clickjacking attack. Here, the idea is to trick the user into clicking on a sensitive UI element. For example, an app might do that by making these access control gadgets transparent, overlaying them on top of something that the user might be more likely to click on, like the Start Game button. And then when the user thinks they're clicking on the Start Game button, they're actually clicking on the overlaid transparent access control gadget and unknowingly granting resource access. There are many other attacks like this that applications can carry out for the same goal. The high-level point I want to make here is just that the operating system needs to protect these access control gadgets from potentially malicious parent applications. In my initial work on user-driven access control, I implemented and secured ACGs within Microsoft Research's ServiceOS browser operating system. But I'm actually going to defer a more in-depth discussion of how we secure access control gadgets, because it turns out that security at the level of the user interface is another research direction in its own right, and I'll be focusing on that in the third part of the talk. A couple of evaluation highlights from the user-driven access control work. I already mentioned our user study, which showed that user-driven access control better matches user expectations with respect to resource access. We also evaluated with respect to security. We looked at existing vulnerabilities in both Chrome and Firefox. And if we focus on specifically those vulnerabilities that are related to resource access, then we find that user-driven access control actually eliminates many of them by design. And I'd be happy to talk in more detail later about what we do and don't fix here with user-driven access control. Finally, to come back to this question of application customization, we looked at top Android applications, and we found that actually many applications have already converged to canonicalized representations of many of these resource-related UIs. For example, here's the microphone resource, the microphone button. Many applications have similar representations, and these applications wouldn't be significantly affected by having to choose from a more limited set of access control gadgets. For those applications that do need more full customization, we could imagine introducing some sort of App Store review process for new gadgets. And in general, we explored some other design points in between those two extremes. In the second part of the talk, I told you about access control as a fundamental problem in the smartphone ecosystem. Existing permission granting approaches were both too permissive and not usable, so they still allowed applications to do things like secretly send costly SMS messages, even when the user isn't doing anything related in the UI. In our work, we explored user-driven access control as an approach that both improves security and better matches user expectations. I really like this user-driven access control approach because I think it's a great example of how we can improve security by changing the system to better match the user's mental model rather than the other way around. Now, in the third part of the talk, I'd like to dive a little bit more deeply into this question of how we actually secure access control gadgets. Because it turns out that this question of how we think about system security at the level of the user interface is a whole research direction in its own right. I just left you hanging with respect to how we secure these access control gadgets from potentially malicious parents. And in our initial user-driven access control prototype, we addressed these issues in a somewhat more ad hoc way. But stepping back, it turns out that this is actually just an example of a much broader problem that comes up in a lot of different contexts. Specifically, modern web and smartphone applications commonly embed user interface elements that were implemented by different developers. For example, here is a mock smartphone application that includes not only its own code, but also the code from an ad library that's providing the ad, the Google library that's providing a map, and maybe the Facebook library, which is providing that like button. Let me show you a couple of things that can go wrong if these different parts of the user interface are mutually distrusting, and if the system doesn't think about security at the level of the user interface. I already mentioned the clickjacking attack in the context of access control gadgets. Again, here you could imagine that a malicious application developer who's trying to increase their ad revenue might try to trick the user into clicking on the ad by, say, making the ad transparent and enticing the user to click on something underneath. A much easier way to do that is to literally programmatically click on the ad UI element object. And that's actually possible in Android today. I prototyped it, and it's easy to do and easy to hide from the user. Another attack is an input eavesdropping attack. Imagine that you're entering your home address or some other sensitive location into that Maps UI. In the way that today's UIs are constructed, there's nothing preventing other elements in the user interface from eavesdropping on that sensitive input. And a final example is the display takeover attack. So similar to a pop-up on the web, you can imagine that a malicious ad tries to take over the screen with a disruptive full-screen advertisement. It turns out that most existing user interface toolkits and many systems, including Android, don't adequately consider security at the level of the user interface or address these kinds of issues. If you're familiar with web security, you might know that browsers actually do provide reasonable security for third-party content that's embedded inside iframes. But those security properties evolved over time and in an ad hoc way. So I wanted to think about this from a more principled way and also specifically provide secure UI embedding for Android. So I approached this problem of security in the user interface in two directions. First, from the perspective of architecting a user interface toolkit that considers security as a first-order goal. In the context of that work, we developed a set of security requirements for embedded user interfaces and a set of system-agnostic techniques to achieve those requirements. And this work was actually published at WIST, which is not a security venue. And it was interesting because it challenged some of the assumptions in existing user interface toolkits that often assume that developers have full control of an interface. From the other direction, I considered a more system-building approach. So how do we actually implement these techniques in a real system, in this case in Android? That led me to implement and release LayerCake, which is a modified version of Android that securely supports cross-application UI embedding. And I'd like to briefly walk you through some of the important design points of LayerCake to give you a flavor of the techniques that we developed. First, just a little bit of background on Android to get us all on the same page. In an Android application, the UI is contained inside of what's called an activity. The activity takes up the whole screen, so here I've outlined the main activity of the calculator application. An assumption that's fundamentally built into Android is that there's only one activity running and in the foreground at a time. So if you're navigating between different views inside an application, you're probably navigating between different activities. This activity then contains a bunch of UI elements. In Android terminology, those are called views. So here's a view of type button, for example. And under the hood, these UI elements are arranged logically in a tree based on their embedding relationships. And in Android, they're drawn inside of a window. One final important thing to understand about Android is that if an application includes third-party content, like, say, a third-party ad, it does that by including the third-party library in its own application. So the ad library, for example, runs in the execution context of the parent application. And that means that certain security vulnerabilities arise, like the ability for the parent and the child to directly manipulate each other's UI elements. Again, if you're familiar with web security, this is a fundamentally different model from that. In Layer Cake, my goal was to securely support cross-application, cross-principal embedding on Android. This is a screenshot of Layer Cake, and I've outlined some different UI elements. And those are actually running in different applications in Layer Cake. Again, in stock Android, these would all be running inside the same application, inside the same execution context. Implementing these techniques in Layer Cake required about 2,500 changes across 50 files in Android 4.2. And I'll walk you through the two most important high-level changes that I made to get this to work. The first step in supporting cross-application content embedding is to separate the embedded content out into its own process. Conceptually, you can think of this a little bit as iframes for Android. In other words, we want the parent activity to be able to embed a child activity that's running entirely in a separate application. That required a number of changes to Android, including, of course, exposing a developer API to let developers actually do this embedding. But more fundamentally, it required changing this embedded assumption in Android that activities can only be running one at a time. Now we need both the parent activity and the child activity to be running simultaneously. And more than that, we need their life cycles to be linked. So if the parent pauses, for example, so does the child. The high-level point with process separation is that it prevents direct UI manipulation attacks. No longer can the child activity directly manipulate the UI element objects of the parent and vice versa. Separating this content out into its own process seems pretty straightforward. But it turns out that separate processes are not sufficient for security at the level of the user interface. To understand that, we need to understand a little bit more about how the layout tree of the user interface works. So naively, what we might do if we want to combine these two activities, the green child and the blue parent, is to literally nest their UI layout trees together. So we would take these green nodes at the bottom and nest them as children of the blue nodes, because they're nested inside of the blue area in the visual view. Unfortunately, that raises some additional security vulnerabilities. In particular, the way that user input is generally handled is that it propagates down through this UI layout tree. What that means is that if there are untrusted nodes anywhere on the path down the tree, they can eavesdrop on, modify, or even block input as it's propagating downward. So in fact, literally nesting these UI layout trees is not what Layer Cake does. Instead, what I implemented upholds an invariant that we developed in our earlier UI toolkit work, that there should be a trusted path down this tree from the root to every node. The key to Layer Cake's activity embedding mechanism is that rather than literally combining these UI layout trees, it separates the child out into its own Android window just as if it was a standalone activity. Of course, the reason we had this UI layout tree nesting in the first place is because we have a visual relationship between the parent and the child. So now in Android, we need the window manager to explicitly keep track of these parent-child relationships and visually overlay the child window on top of the parent window in the right size and at the right location. In other words, we can achieve the same visual effect as if we had literally nested these two UI layout trees, but by keeping them separate, we can prevent these input eavesdropping and denial of service attacks. We evaluated layer cake in a couple of ways, including performance. I'd be happy to tell you about that later if you're interested. Today, I want to talk about some of the functionality that layer cake can support that we actually can't support securely on stock Android. I've already talked a little bit about the ad example. Again, in stock Android, ads are running in the application's own process, and that leads to some security vulnerabilities. In layer cake, they're running in separate processes, and the advertisement is simply visually overlaid. Similarly, we can now support secure embedded Facebook widgets. Those are actually not officially supported with Facebook's Android SDK, possibly because of some of these security in the UI issues. But with layer cake, we can now support them. Popping all the way back up to access control gadgets, with the techniques implemented in layer cake, it's actually now almost trivial to add access control gadgets to Android and fundamentally improve the permission granting model. In our work, we also developed a number of additional techniques for user interface level security. Both techniques specifically targeted at security, so targeting different classes of attacks, or techniques for flexibility that still allow developers to flexibly implement the range of interfaces that they might like to. In this third part of the talk, I dove more deeply into this problem of security in the user interface. This exploration was initially triggered by the need to secure access control gadgets, but turned out to be a much bigger problem that affects smartphone and web user interfaces. So we developed a set of UI-level security techniques and requirements that I then implemented and refined in layer cake, a modified version of Android that securely supports cross-application embedding. Before I conclude the talk, I wanted to briefly mention a few of the other things that I've worked on over the last few years. Like I mentioned, my research interests are very broad, and one of the things that I really love about security is that it lets me look at different technologies and touch different aspects of computer science. So let me just briefly give you a couple of other examples. Many of you are probably familiar with our work on automotive security. This was a collaboration with UCSD, in which we found that not only are automotive systems exploitable remotely, like over the cellular network, but any such compromise can lead to full control of the vehicle, including the ability to control the brakes. And that work led to a real shift in how automotive manufacturers and other organizations think about automotive security. I've also explored user mental models in other contexts. For example, I recently became interested in the Snapchat smartphone application, which lets you send disappearing messages. It turns out that Snapchat is actually not secure. It doesn't securely delete those messages. And I was interested in whether people know that and whether and how that affects how they use the application. So we found some interesting things in our user study that I'd be happy to talk more about with you later. As a last example, I'd like to briefly talk about emerging security and privacy challenges with wearable and augmented reality technologies. Augmented reality technologies are already shipping commercially today, like in the form of smartphone applications like WordLens, which is an in-image real-time translation application. Or on the hardware side, many of you are probably familiar with Google Glass, Google's augmented reality glasses. A couple of years ago, before Glass was even announced, I started becoming interested in the emerging security and privacy challenges in this space. And so my collaborators and I have been among the first to map out and start tackling some of the challenges here. And we have an article coming out in CACM, I think next month, that lays out a research agenda in this space. I'm not just interested in the challenges that augmented reality will present, but also in ways in which it can help us think about existing security and privacy challenges in new ways. To give you just one example, password usability is a well-known problem in many systems. And so as an example of how we might think about that in a different way with augmented reality, I prototyped an augmented reality password manager for Google Glass, which you can see there on the right. These technologies are still changing rapidly, and we've only just begun to understand and address the challenges in this space. So I think there's a lot of interesting work to be done here, and it's especially exciting because now's the time when we can still positively influence the designs of these technologies before they become widespread. Today I've described in more detail just a subset of my work. I've told you about two important ways in which users' mental models don't match the reality of today's systems, and how we can address that by changing the systems to better match the mental models. I talked about privacy on the web from third-party tracking, where we found the prevalence of personal trackers like Facebook, Google, and Twitter, and developed Share Me Not as a novel defense. I talked about permission granting in the context of modern operating systems like smartphones, where we developed user-driven access control as a more secure model that better matches user expectations. User-driven access control relied on these access control gadgets, which in turn relied on security at the level of the user interface. And I dove more deeply into that in the third part of the talk. As new technologies become widely adopted, they not only improve and transform our lives, but they also bring with them new and serious security and privacy concerns. But I hope I've shown you today that with the right insights, we can improve security and privacy in these technologies, both existing and emerging technologies, before they become widespread. Like I said, my research interests within security are broad, and I've given you a flavor today of some of the different techniques that I use, including user studies, real-world measurements, and building and deploying systems like Share Me Not and Layer Cake. And I'm excited to understand and tackle new security and privacy challenges in new domains going forward. And I'd be happy to answer any of your questions now. Thank you. Yeah, Paul.
So one of the ways one might assume that one, as a naive user would be, well, I'll run some sort of ad blocker, and so the ad blocker knows, because it might know my history, but maybe I trust them as opposed to Criteo or something like that. Does that, how does that fit into the kinds of things you're doing, and how is it not fail to do the kinds of things?
Yeah, so the question is about ad blockers and other kinds of defenses. There are certainly existing client-side defenses that people can use, like ad blockers or other tracker blockers like Ghostry. There are two challenges with those. One is that, of course, in the long term, trackers could move to using non-client-side mechanisms, especially if they're collaborating or colluding with the parent sites. They could just do it all on the back end. That's one long-term challenge there. In the shorter term, the way all of these tracking, blocking things work is they use blacklists, which are often incomplete, and sometimes it turns out that advertising companies own some of these. So actually, some of the measurement tool that I built, which detects trackers based on client-side behaviors, I didn't talk about it today, but I turned into a platform called Tracking Observer, and the idea there is that it exposes APIs that allows you to build a tracking blocking tool on top of it so that you're not relying on a potentially flawed blacklist.
Yes, so some people say that privacy doesn't sell. Nobody pays for privacy. I wonder if you had any comments about what incentive companies might have to adopt some of the privacy protecting technology that you developed.
Yeah, so the question is about what incentive companies have to adopt the privacy preserving technology. That's a good question. I think privacy can be challenging in that way because even users, if they don't see the effects of what it is that they're losing, nothing bad happens to them. And frankly, most people, your browsing history isn't that sensitive. You can probably guess which sites I go to. I think the bigger picture with privacy is that we want to understand what's happening in the ecosystem, like in the tracking ecosystem, so that we can give users visibility and options if they want to opt out of it. And maybe not just individual users, but organizations like the Electronic Frontier Foundation that can influence policy discussions. Often, certainly in some cases you might argue that companies themselves have an incentive to be the company that better preserves your privacy and attract people that way. the other side of that is that policy sometimes mandates that.
If you have a system that's entirely opt-out, doesn't that create security problems of its own? I mean, if everyone is opting out, but a select few people are opting out in certain situations, doesn't that sort of arise suspicion, or couldn't it be used against?
Right. So the question is kind of like if you're the only one, you can't be anonymous by yourself, kind of. Yeah. Yeah, I mean, certainly that's true. I think that's a good question. I don't know exactly in the tracking space. I think there's enough concern about privacy in general that doesn't have to, on the web, especially given NSA revelations, that it doesn't necessarily mean that you are doing something bad, that you care about your privacy. But you're right that in general, that's you want to be careful not to build systems that the only people using are exposing themselves.
So a savvy user can install your plugin, install AdBlock, disable third-party cookies, etc. But most people aren't going to do any of that stuff. Do you know if there's been any work towards integrating this sort of stuff with browsers or
Yeah. So the question is about non-savvy users won't explicitly go and install plugins. Has there been any work in integrating this into the browser? And the answer is yes, actually. So the do not track effort was partly that. So what do not track is it's a browser setting that was adopted by, I think, almost all browsers that you select, and you say, I don't want to be tracked. And then with every request, you basically send do not track equals 1. And the idea is that trackers are supposed to honor that, and that policy discussions were supposed to support the requirement to honor that setting. Unfortunately, it turns out that those policy discussions have not been as effective because I think because the economic incentives are challenging and the advertisers, are a strong stakeholder. So there hasn't been any, other than third-party cookie blocking, there hasn't been any technical defenses built into browsers. But I wouldn't be surprised if more of that happens. Like some of the Mozilla is behind some of the efforts to do tracking detection and so on, for example. Yeah.
Suppose somebody was really grumpy about this, maybe not here. Would another defense be to flood the trackers with so much bogus information that it became useless?
Yeah, so the question is, could we just flood the trackers with bogus information until it becomes useless? I think that we could certainly do that. I don't know. I mean, you'd have to be careful that you were actually getting the guarantees you were looking for. And you might have other side effects like performance issues. But certainly hiding in a set of things, that's not a bad idea.
Okay, final question.
All this big data is very valuable to marketers and product designers because they can design better products and market it efficiently. So in your research, have you seen if these marketers and product designers would be more open to getting data directly from users or asking for data openly rather than buying it from the brokers who obviously we don't buy?
Yeah, so the question is, would marketers and so on be more interested in getting data directly from users instead of sort of through the tracking channel? I don't know. I haven't seen anything specifically on that. I know some people have looked a little bit at how much people would be willing to sell their information for and so on. But I don't know anything. I haven't looked into that specific thing. That's interesting.
Okay, let's thank Franzi. We know where she sits, so we can ask her questions afterwards.